that I was studying electronic engineering. And so he made this comment. He said, "Oh, so you'll become a project manager." And so I was a little bit offended by this, that he would think that just because I'm studying electrical or electronic engineering that I would become a project manager. But he had an understanding of industry that I did not have at that stage. At another time, when I was doing holiday work for my bursary company back home in Namibia, I asked an engineer whether he used any of the mathematics that he did at university. And he thought for a little while, and then he said, yes, but sometimes things that you wouldn't even expect, like number conversions. And so I thought, number conversions. Am I really studying 4 years at university to learn how to convert meters to kilometers? And so the sad reality is that many young people who enroll for a degree in engineering because of their passion for design and for solving complex problems get to industry and are sometimes disappointed when they find that the real world engineering environment doesn't always involve those in-depth design skills that they were taught at university. And I suspect that this is a particularly big challenge in developing countries such as Namibia and South Africa. Of course, we do have research and development companies doing very exciting high-tech design work, but these are still relatively few and far between. And especially in electronics, and even more so in antennas and telecommunications. Most telecommunications technologies here are imported. And it's mostly only in the defense industry that you do find some companies doing really, really exciting high-tech R&D work related to antennas or communications. Unfortunately, I suspect that here in Southern Africa, perhaps even the majority of electrical engineering graduates do not end up doing the kind of in-depth design work that they were trained for. For those who do get engineering jobs, many end up as project managers in procurement, in maintenance and repair. Some end up basically becoming operators, and others are effectively employed as bureaucrats. If you're lucky, like me, then you might get to do some basic design work combined with practical installation, commissioning, and maintenance. So when you choose engineering because of your passion for designing new things and for solving complex problems, this reality can be a little bit discouraging. I did not end with my undergraduate degree though, but after finishing my undergraduate degree in electronic engineering, I immediately started with my postgraduate studies. And my bursary company gave me time off, which I'm very grateful for. And about 4 years later, I had completed my PhD in electronics, specializing in antenna array design. While doing my PhD, I met the same electrical engineer who had called me a project manager. And when he heard that I was doing my PhD, he didn't have anything to say. I also didn't have anything to say because, to be honest, I wasn't really sure what I was going to do with a PhD in engineering, but I just knew that I had a passion for research and design and that I had to pursue this, whether it ended up being a good career choice or not. And if it wasn't for the fact that I already had employment with my bursary company, I'm honestly not sure how easy it would have been for me to find a job in Namibia with a PhD. So I have to be honest and say that when I started at my bursary company, I was not too excited about the kind of work that I was going to be doing. And my bursary company is Namibia Water Corporation, or NamWater, and I joined them in 2019 after completing my PhD. And I was employed in a communications subdivision where we mainly do telemetry or the remote monitoring of water infrastructure across the country. Now, Namibia is a vast and a sparsely populated country in Southern Africa, and we mostly make use of our own UHF data networks to transfer data from remote stations across the country, and in some cases we also make use of the cell phone network. My day-to-day work currently involves procuring telemetry and components, designing SCADA human-machine interfaces for monitoring these systems, and installing, maintaining, and commissioning telemetry systems that include radios and antennas. So in order to make the best use of the 4 years that I have to work back for my bursary company, I decided to set the goal for myself of registering with the engineering councils of both Namibia and South Africa, because I felt like I needed to have a goal to work towards. And I wanted to register in South Africa as well because Namibia is not a signatory to international engineering agreements like South Africa. And I was actually lucky because the kind of practical hands-on experience that I was gaining at NamWater turned out to be perfect for registration. And going through this process of registration, and in particular, looking at my work through the lens of the broader aspects of the engineering profession, really changed my view of engineering itself. And it really changed my attitude towards my work, which was negative to start off with. And I went from just trying to do my time, as it were, at NamWater, to really developing an appreciation for the practical engineering skills that I was learning. Before, I used to think of engineering mainly in terms of design and discovery. But through my time in industry, I realized that engineering is actually much broader than just design. I was always looking for complex problems to solve, but I realized that in a practical engineering environment, the issues that are complex are not just design issues. While discussing the issue of demonstrating complexity for professional registration, a civil engineer, Robert Blith, wrote the following in the South African Civil Engineering magazine. He said, quote, "There was always a general belief that complexity needs to be demonstrated primarily in respect of the technical complexity of a project. Not always easy to do. Experienced engineers will tell you that complexity covers a much wider aspect of projects, and that the technical issues may not, in fact, always be complex. What about the complexities of social issues, financing, political constraints and policies, economic justification, and other less defined issues?" End quote. So even though I still do want to go back into research, recognizing the complexity of engineering in its broader scope really helped me to make the best of my time in industry so far, and to learn some of the skills that I don't believe I would have been able to learn in any other way. In this talk, I'd like to share some principles that will help you to go from new to old. I mean, from a high-tech academic environment where you learn the latest technologies, state-of-the-art systems, to a practical engineering environment where old, tried and tested technologies are being applied. I'd like to share some of the lessons that I've learned in industry and look at the broader scope of the engineering profession. And in particular, I'd like to help you see how adopting the right mindset helps you to get the maximum benefit from your time in a practical engineering environment. The key is to realize that complexity does not only lie in design. The main thesis of my talk today is that simple things become complex in a real-world environment. Simple things become complex in a real-world environment. When you realize this fact, you will not be bored. When you are actively on the lookout for these broader complex issues, instead of just trying to get by doing the minimum work required, that is when you really start learning the most valuable practical engineering skills that you can apply almost anywhere in life. But before we look at the differences between academia and industry, we first need to take a step back and ask, what is engineering really? In most countries, engineering is a profession. In other words, a discipline that is regulated for the protection and benefit of society, just like the medical or the legal profession. Engineering in this case covers professional, or in some countries, chartered engineers, technologists, or in some countries, incorporated engineers, and technicians. And practicing independently usually requires one to complete some practical years of training. Now, each country has its own standard for evaluating the competence of professional engineers for registration, but countries that are members of the International Professional Engineers Agreement, in the case of professional or chartered engineers, recognize that the standards are essentially equivalent. Now, South Africa, where I'm registered as a professional engineer, and Malaysia are both members of this agreement. And I was quite impressed to see that Malaysia is a member of all of the agreements that are international agreements related to engineering. So in order to get a definition of engineering as a profession, therefore, let's have a look at the professional competencies set out by the International Engineering Alliance, which facilitates this agreement. The International Engineering Alliance outlines 13 competencies that engineering professionals must be able to demonstrate. These competencies are applicable at all levels, from professional engineer to technician, but they differ in scope. And so I will be giving the definitions as an example for the case of professional engineers. Firstly, comprehend and apply universal knowledge. That is, comprehend and apply advanced knowledge of the widely applied principles underpinning good practice. Number two, comprehend and apply local knowledge. Comprehend and apply advanced knowledge of the widely applied principles underpinning good practice specific to the jurisdiction of practice. Number three, problem analysis. Find, investigate, and analyze complex problems using data and information technologies where applicable. Number four, design and development of solutions. Design or develop solutions to complex problems considering a variety of perspectives and taking account of stakeholder views. Number five, evaluation. Evaluate the outcomes and impacts of complex activities. Number six, protection of society. Recognize the foreseeable economic, social, and environmental effects of complex activities and seek to achieve sustainable outcomes. Number seven, legal, regulatory, and cultural. Meet all legal, regulatory, and cultural requirements and protect public health and safety in the course of all activities. Number eight, ethics. Conduct activities ethically. Number nine, manage engineering activities. Manage part or all of one or more complex activities. Number 10, communication and collaboration. Communicate and collaborate using multiple media clearly and inclusively with a broad range of stakeholders in the course of all activities. Number 11, continuing professional development or CPD and lifelong learning. Undertake CPD activities to maintain and extend competences and enhance the ability to adapt to emerging technologies and the ever-changing nature of work. Number 12, judgment. Recognize complexity and assess alternatives in light of competing requirements and incomplete knowledge. Exercise sound judgment in the course of all complex activities. And number 13, responsibility for decisions. Be responsible for making decisions on part or all of complex activities. When we study engineering at university, we often think of engineering in terms of the first four competencies, namely knowledge and problem solving. But the other 9 competencies represent the broader scope of the engineering profession, which can only really be developed fully by means of practical experience. In South Africa, for example, even university lecturers generally need to do some consulting work in addition to the lecturing in order to gain the practical experience required for registration, even though some aspects of lecturing can count as practical experience, for example, managing a laboratory. When I started viewing my industry experience in light of these requirements in order to prepare my application for professional registration, I started recognizing the complexity of these broader issues, and I started realizing that engineering is not only difficult because it is technically challenging, but engineering is complex because of all the different real-world implications that need to be taken into account when practicing engineering. I'd like to take you through a few different experiences that I've had in industry so far, and firstly highlight a few key lessons that I've learned, and secondly highlight some key differences between academia and industry that one needs to be aware of. And hopefully some of these principles will help those of you who find yourselves in industry to make the best of that. The first example from my experience is a proof of concept versus a real-world pilot project. As part of my PhD, I designed a new type of antenna system. I did not only do a theoretical design, but I manufactured a prototype, which you can see here. This is a so-called compressive antenna array, where the feed network in the middle takes a 4-element antenna array at the top and produces only 2 outputs or subarrays at the bottom. So I did gain some practical experience in my PhD, but it was still very different from the kind of practical experience that I gained in industry. When I started working at NamWater, my first task was to design a new server power backup system for our SCADA servers, which we use to monitor our water supply infrastructure across the country. These SCADA servers are crucial to water supply infrastructure for operations and also to log data for long-term planning. And because of the relatively poor power quality and reliability in many areas of Namibia, a reliable server power backup system was required. And I was given two main requirements. Firstly, that this backup system was to provide backup for 2 days, give enough time for somebody to travel to site. And secondly, the backup system should require minimal human intervention and should be monitored remotely from the headquarters in Windhoek, the capital. So the idea was quite simple. Take off-the-shelf chargers and off-the-shelf inverters and connect them to off-the-shelf batteries. And compared to the PhD that I had just completed, I thought, wow, this is a really simple assignment. However, the requirement of reliability made this problem significantly more complex than I originally thought. To start off with, I proposed a redundant system composed of 2 independent backup systems. So this meant that the system would not fail if any single component in the system failed, but it also meant that you wouldn't know if a single component failed if you did not monitor it. And so everything had to be monitored in detail. The mains power, every circuit breaker, every earth leakage breaker, every charger, inverter, every battery cell, Ethernet and serial gateways and switches, even the room temperature had to be monitored. And so in total, I ended up monitoring 113 different variables, including 19 different voltages, 12 currents, 8 powers, 7 temperatures, 16 states, and 45 different alarms. So even though I was only connecting off-the-shelf devices together, integrating devices from different brands actually proved to be quite challenging. For example, there was no easy way for me to determine whether the batteries were still there, because unfortunately the battery itself couldn't tell whether its circuit breaker was on or off. And there was no easy way to customize it without voiding the warranty. So the chargers would ensure that there was always 52 volts DC on the bus. And so you couldn't just check for the battery voltage because the chargers were supplying that voltage. And so I had to develop an automated procedure to check where I switch the chargers off for 1 minute every hour, just in order to test if the battery voltage is still there. And so there were therefore more than enough interesting challenges, even though I was simply connecting off-the-shelf devices together. And the incredible level of reliability that was required goes back to the importance of these SCADA servers. We definitely don't use this kind of backup system for everyday computers. These servers are crucial for long-term and the short term. For example, starting and stopping pumps was part of the operations, as well as the logging of data for long-term planning. I therefore had to develop an appreciation for the impact of this engineering activity, which falls under IEA competency number 5, evaluation of impacts, and number 6, protection of society. While I was reading through the Engineering Council of South Africa's documentation, I kept coming across this word sustainability. And they gave the example of relying on an unsustainable raw material that might not be available in future. And so I try to think, how does this word sustainability come into my work? And I realized that in this case, a sustainable design meant making sure that the unavailability of one particular component does not necessitate a major redesign of the system, because that could be very costly in the future. And this is particularly important when you realize that the design service life for this system was at least 10 years. So I had to choose components today that would be available, or at least for which I would be able to find alternatives in 10 years' time. And already this has been tested since I installed the first pilot system only a year and a half ago. The particular battery model that I chose was discontinued, but I could easily choose another battery model because I chose 19-inch rack mount batteries, of which there are many different types available on the market. Now, this 19-inch server rack format has been used for at least the last 100 years. Secondly, the logger that is central to the design will unfortunately soon be discontinued because of the global chip shortage. But again, I will easily be able to replace it with another one since I use the industry standard Modbus protocol for getting the data from the other devices. And for those devices without Modbus capabilities, I use simple dry contacts, for example, relays for alarm signaling. Now, the Modbus protocol has been around for the last 40 years. The least flexible design choice that I made was the particular brand of chargers and inverters, since I would not be able to easily switch over to another brand with the level of monitoring that I have in the system. And for that reason, I chose a brand with 50 years, almost 50 years of experience in designing power devices for rugged and remote environments. And so do you see how the word old is coming in here? Reliability is ensured not necessarily by choosing the latest and the most innovative technologies, but rather those old standards, those old protocols, and those old companies that have proven themselves over multiple decades. The battery chemistry used is the latest in terms of what is commercially available, but it's still a mature technology that was first proposed 26 years ago. However, it's not only the design that ended up being more complex than I thought, but also the management of the pilot project. And management falls under IEA Competency 9, Managing Engineering Activities. In this case, I had to manage the procurement, which included well over 100 unique components, a workshop assembly, the site installation with a team of artisans, the commissioning, the initial maintenance, and now the rollout of the design to other sites. So let's look at some of the differences between my PhD prototype and my server backup design. Firstly, the scope of the compressive array prototype from my PhD was a proof of concept, whereas the scope of the server backup was a real-world pilot project for one location followed by medium-scale implementation to multiple locations. The maturity of the technology used in the compressive array was experimental, and the point of the prototype was simply to demonstrate that a theoretical idea could be feasible to implement in practice, whereas the server backup used mature technologies that had been proven over multiple decades. In terms of the components used, the compressive array used a custom-designed PCB, whereas the server backup integrated off-the-shelf devices. Not even components, but complete devices, which presented its own challenges due to lack of customizability. In terms of volume, the compressive array was a single prototype, but the server backup system was a single pilot, which will be followed out by rollout to 15 sites, which is still relatively small. In terms of service life, there was no service life associated with the compressive array, and it literally only had to work once during testing. So I even used a bare copper finish since I knew that the device would not be used again, instead of using an anti-corrosion finish. Whereas the service life of the server backup, on the other hand, was more than 10 years. The compressive array had no requirements in terms of reliability, whereas the server backup was expected to have a mean time between failures in the order of years, which means that it should only fail every few years at the least. One can see that, therefore, as volume and reliability requirements go up, the challenges move from having to do more with the fundamental technology itself to having more to do with the implementation. And this brings us to our first lesson, that a simple design becomes complex when designing for real-world implementation. That goes for both the design itself and managing its real-world implementation as a project. And the first key difference between academia and industry demonstrated here is that prototypes are technologically complex, but real-world designs are complex in implementation. I highly recommend Mike Golio's article, Technology Maturity and Other Hurdles, from a 2020 edition of the IEEE Microwave magazine for an insightful overview of the spectrum of technology maturity from proof of concept to mass consumer manufacturing. That's technology maturity and other hurdles. The second example from my experience in industry is about collaboration across domains. At the end of my first year in industry, I had the privilege of being responsible for the telemetry component of a containerized reverse osmosis water treatment plant. The plant was installed by a contractor, and it was my responsibility to connect it to our system and to create a SCADA human machine interface, or HMI, so that you could monitor the water treatment plant remotely. And the HMI is a page that gives you a graphical overview of the plant and allows you to see all the key measurements. At that stage, I knew nothing about process engineering or reverse osmosis, so it was difficult for me even to read the process and instrumentation diagrams, or P&IDs, which are the drawings that show how all the equipments and the instruments are connected together. I had to learn how the reverse osmosis process works so that I could draw that HMI page accurately, and I only had about a month to prepare. When I went to site, the process engineer wasn't there yet, and there was a technician from the contractor who was struggling to figure something out. And by that stage, after barely a month, I had enough knowledge of the plant to be able to explain something about how the plant works to him. So even though for a chemical engineer or process engineer, the working of a reverse osmosis plant might be relatively simple, for me, it was complex and interesting simply because it was something new and in a different field that I knew nothing about. And so this taught me our second lesson, that a simple concept becomes complex when it's in a foreign domain. And by this, I simply mean that something might not be at the forefront of technological innovation, and yet it can still be complex and interesting for you if it's not in your domain. So if you find yourself in a work environment where you're not particularly stimulated by your own field, then look further and be curious about other domains. When you work on a project with somebody from a different discipline, I mean, even if you speak to your HR officer or somebody from accounting, be curious and ask questions and use the opportunity to learn something new and make life interesting. For them, what they are doing might be old news to them, and what you are doing might be old news to you. But to each other, you have the opportunity to teach and to learn something new. Industry often provides unique opportunities for collaboration across domains, and this speaks to IEA competency number 10, collaboration and communication. When I commissioned the reverse osmosis plant with the process engineer, I honestly had so much fun, even as we sat almost until midnight to finish the work. And in the process, you also form that human connection. And this brings us to our second key difference between academia and industry, namely that research is more specialist, but industry is more generalist. Of course, there are opportunities for collaboration in academia as well, and you can apply these same principles there. But in general, industry teaches you a broader range of skills, which can be extremely beneficial further down your career path. For those of you who are in academia and perhaps frustrated by an environment that is too narrow and specialized, in my other ambassador talk, From Old to New, I talk about the benefits of being both a specialist and a generalist and how that can benefit your research, and how even in an academic environment, having a broad range of interests is not necessarily a bad thing. The third example from my experience is about assessing alternatives in the light of real-world requirements. At each of our radio frequency or RF outstations, we have a radio connected via coaxial cable to an antenna, and then some RF components in between. And so in order to do maintenance and fault finding on these RF systems, we used to use what's called a watt meter or an RF power meter. So it's an analog instrument that you place somewhere along the RF line, and then you can measure the power in the forward direction and also the power being reflected back, which can indicate a potential issue. And so I was tasked with replacing our old watt meters that were almost all broken. Now, the watt meters that we used to use appeared rugged, but in fact, we found that they actually easily got damaged in the field. And so for this reason, I decided only to consider alternatives that were rated to the environmental specification MIL PRF 28800F Class 2, which is a measurable way of confirming that a test instrument is indeed suitable for rugged environments in terms of shock, vibration, and temperature, for example. So I decided to go for a cable and antenna tester, which is a more advanced test instrument. And it's basically a one-port vector network analyzer that allows you to do what's called a line sweep from the ground, which you can then use to pinpoint exactly at which distance a fault occurs along any point of the RF system from only a single measurement from the ground. So I needed to choose two components: a power sensor to measure the power from the radio, and a cable and antenna analyzer with this line sweep or distance to fault functionality. Now, many of the cable and antenna analyzers do actually have an internal power sensor, but with limited accuracy. And up to that point, we specified that during maintenance visits, our radio powers should be correct within plus minus 10% or about 0.4 dB. But these internal power sensors that were included within the antenna analyzers were typically only accurate about plus minus 1 dB. So I looked at more accurate external power sensors that could be used with the cable and antenna tester, but they were all quite expensive and sometimes even about half the cost of the cable and antenna tester itself. And also, I could not find an external power sensor that was rated to our environmental specification and the mil spec, and the ones that I did find did not cover our required frequency range. So there was therefore no solution that met our seemingly conflicting requirements of the high sensor accuracy as well as ruggedness. And so I had to compromise on one of these two. I had to take a step back and ask myself, what is the need really? The need was actually not to accurately measure the power of a radio, but it was actually simply to confirm whether a radio was still in a good working condition or not. And so for this need, an accuracy of plus minus 1 dB was actually more than sufficient. And so I chose a rugged cable and antenna tester with an internal power sensor, since this met our true need. And this brings me to our third lesson, namely, that a simple choice becomes complex in light of conflicting real-world requirements. Purchasing a new test instrument at first seemed again like a very simple task, but the real-world requirement for a rugged test instrument made the whole task significantly more complex, and it took me a long time to reach the chosen solution. This decision required judgment, which is defined by IEA Competency 12 judgment as including recognizing complexity and assessing alternatives in light of competing requirements. When you study engineering, you might think that at its core, engineering is about making complex calculations because of all the mathematics that you learn. But in reality, the process of assessing alternatives and making decisions informed by engineering principles, whether design decisions or other types of decisions, is often closer to the heart of engineering problem solving. And in order to do this properly, an incredibly important skill is to be able to identify the real need that informs the requirements and the specifications. As engineers, it's almost like we're wired to jump to solutions, even before we properly understand the problem. And this tendency of ours to immediately start identifying solutions is both a strong point and also a weakness that we need to be aware of. I was searching for a power sensor accurate to plus minus 10% without ever stopping to think where that specification came from and how it related to our actual need. It would have been a very poor decision to compromise on the requirement for ruggedness, which was very important, in favor of a power sensor that was more accurate than we really needed. And so in industry, therefore, it is crucial to understand the need and to make sure, as Jeffrey Pinto would say, that you are dealing with a need in search of a solution and not a solution in search of a need. This is much more important in industry than in academia, where there's more freedom to explore research questions simply because they are interesting and new. Often in research, you might discover a solution before you know what problem it solves, and this is often how technology progresses. But unless you are in a research and development environment where you are specifically given the freedom to explore topics based on your curiosity, in industry, you need to discipline yourself to focus on the need and make sure that you address that. And so our third key difference between academia and industry is that research is solution first, but industry is problem first. That is, research focuses on developing new solutions because they are new and interesting, but industry focuses more on solving real world problems. And you are unfortunately wasting time and money if you're not addressing the real need. Now, of course, this is somewhat oversimplified, but it expresses a difference in the focus between academia and industry. My last example from my experience in industry is about making judgments under real world conditions. Early in my time at NamWater, I had to design a UHF radio link where the telemetry station was about 47 kilometers away from the repeater station. And I used PathLoss 5 software to analyze this link. And so I chose a 12-element Yagi antenna at a height of 8 meters, where I used a 6-meter pole attached to the side of a container. Now, the predicted signal strength was excellent, with a fade margin or margin of safety of about 25 dBs. However, when I wanted to go for installation, a colleague of mine questioned whether my antenna would be high enough because he said that antennas in that station actually struggle with communications often. And so I found it surprising, and I delayed the project until I could gain more clarity. I sent somebody to site to do some field tests, but the results were worse than I calculated, but they were borderline and therefore inconclusive. I had to decide what to do because the project was being delayed. I could not simply use a longer pole because the container would not be able to support that. And a longer pole would require a concrete base, and the civil engineering department advised then that guy wires would be required for such a tall pole. So, in the face of incomplete knowledge, I decided to continue with the original plan and install the antenna as per the original design. And my justification for this was that the potential benefit of the link working outweighed the cost of having to take it down if it didn't work, and that it was worth trying considering the additional cost and delays of having to investigate an alternative solution. So I installed the antenna as originally planned, and the performance was worse than expected, but it was actually still acceptable at the end of the day. So I had to figure out afterwards why there were such huge discrepancies between simulation and measurement. After a lot of investigation and studying, I realized that diffraction was probably the only mechanism that could introduce errors of such magnitudes. This link was not line of sight, but it was obstructed close to the station, which means that the radio waves actually reach the station by diffracting around obstacles. And so one possible factor is the fact that the calculations only take into account a vertical cross-section of the path and does not consider off-path obstructions in the horizontal plane. In this case, the station is located right behind a reservoir on a hill, and the path grazes the side of the hill. And so the peak of the hill is not actually taken into account in the simulation. When I, however, did an area study where you map the signal reception across a whole area, I found that our station was right next to an area of poor reception. And our station was right on the edge of this. So I recommended that we must not rely on point-to-point calculations only, but we must always do an area study and look out for adjacent areas of poor signal reception. And so there were also some other discrepancies that I had to consider. For example, the digital terrain models we used were SRTM, or Shuttle Radar Topography Mission models, which are terrain models generated by radar from space. So our repeater in this case is located on an existing tower 275 meters high. And this tower actually appears in the radar terrain model as a hill 45 meters high. And near the station, there was an unrelated telecommunications tower that also resulted in such a false hill 9 meters high. And so I had to manually remove these hills from the models used in the simulations. So this example shows the importance of understanding the assumptions behind theoretical models and also the importance of the quality of your input data to these models. And that you should not just blindly use an algorithm. Bringing us to the next lesson. And so I'd like to highlight 3 lessons from these experiences. Lesson 4 is that a simple calculation becomes complex when ideal assumptions don't hold. Sometimes it's only in the real world that you discover assumptions that don't hold. And you might never have known about these issues if you only worked with theoretical models. And the corresponding key difference is that theoretical models are based on assumptions, but real-world phenomena do not always obey assumptions. Of course, you can and you should investigate real-world conditions in academic research, but often those in industry are in the best position to identify real-world challenges. And that's why collaboration between academia and industry is so important. Our 5th lesson is that a simple judgment becomes complex in the face of incomplete knowledge. This again refers back to IEA Competency 12, judgment, which specifically mentions assessing alternatives in the context of incomplete knowledge. The key difference here between academia and industry is that unanswered questions in research are future work, whereas real-world decisions need to be made despite unanswered questions. This is one of the key reasons why industry experience is so valuable. Judgment is only really developed when you are forced to make a decision despite not having all the required information. In academia, for example, you will often rephrase the problem if you don't have all the answers, or you can leave some unanswered questions as future work. But in industry, decisions need to be made, whether you have all the information or not, and this is how you develop sound engineering judgment. Lesson 6 is that a simple decision becomes complex when the consequences are real. And with this, I'm not just referring to the judgment or the decision itself, but rather the execution of a decision and taking responsibility for that. And the key difference here is that poor judgment in academia has indirect consequences, whereas poor judgment in industry has direct consequences. Now, of course, poor judgment in research can have devastating effects, but those effects are often more indirect. Now, it's actually incredible how difficult it can be to follow through on a decision when the consequences are real. And this has personally been one of my biggest struggles in industry. I hate uncertainty. And when I have to make a decision when I feel like I don't have all the information, it can really be paralyzing. It's like there's a mountain in front of you, especially if the mistakes are expensive in terms of time and money. And so making that decision and accepting responsibility takes real courage. Now, I can't tell you how to learn courage, apart from the simple fact that you can only learn it through experience. And I think this is by far not only the most challenging aspect of industry, but also one of the biggest advantages of industry experience, that you get to practice your decision-making muscles and you learn the courage to follow through on decisions that have significant consequences. Let's go through our lessons once more. Number 1, a simple design becomes complex when designing for real-world implementation. A simple concept becomes complex when it's in a foreign domain. A simple choice becomes complex in light of conflicting real-world requirements. A simple calculation becomes complex when ideal assumptions don't hold. A simple judgment becomes complex in the face of incomplete knowledge. And a simple decision becomes complex when the consequences are real. In conclusion, when you consider the broader aspects of the engineering profession, you will learn that there's a lot to learn in industry apart from just design. In fact, many, if not most of the skills we talked about today can be applied to any problem-solving environment, not just engineering design. My challenge to both academics and industry professionals, both to specialists and to generalists, is to come together and to learn from one another. I realize how lucky I am that the experience I've been able to acquire at NamWater is uncommonly broad, even by Southern African standards. But I hope that some of the lessons I've shared with you today will help you to identify those opportunities that you do have in your own field and help you realize that the simplest of tasks in a real-world environment are often more complex and more interesting than you might have originally thought. If there's one thing that I've learned, is that there's always something to learn. In my other talk, From Old to New, I focus on the lessons that I learned during my PhD, and in particular, how to apply new ideas to an old and established research domain. And I also reflect on the advantages of having a broad range of interests, even as a specialist. Please follow the IEEE Antennas and Propagation Society Young Professionals on LinkedIn for upcoming talks by myself and other young professional ambassadors, and please feel free to invite me for my other talk. Thank you.
Wow, thank you, Dr. Heinrich, for a very nice talk. So now I open up the floor for any question from members of the floor. Question? Let me check at the chat area. Or there's no comment. To all participants, please don't forget to fill out the form for attendance and set purposes. We will share these recording sessions along with this e-cert. So please fill up this Google form link. So any question? So Dr. Henry, how many years have you how many years have you worked with have you worked as a lecturer and before you entered this industry world?
Thank you. So I actually, when I completed my degree, I started immediately with my postgraduate studies, completed my PhD, and so I never was actually full-time in academia yet. So I was working as an assistant lecturer only when I was doing my PhD. So I've never actually been full-time in academia. I completed my PhD. I've still been doing some research part-time after that, collaborating with my supervisor there. But I have also been lecturing part-time this semester. So a little bit of both, but not full-time.
So in your opinions, as because I'm a lecturer, I mean, like when I teach my students, how actually we try to relate whatever that we teach the students with the industrial world. I mean, like for example, I'm teaching electromagnetic theory, and then I just wanted to know this is important in industry, so that they really capture wherever that we teach. So is it towards the end of the like with the teaching, I should like tell them, or this is the applications, this is what you're going to apply, that you can. So in your opinion, so what should as a lecturer to apply that, so that they said, oh, this theory I can apply in industry later on.
Yes, definitely. I think that's very important, and I think you need to look for those applications. And in my case, for example, in electromagnetics, the one thing that I found, I just happened to find a book in an old bookstore here somewhere that happened to be on the design of microwave links. And it just happened to be perfect because it talks about propagation, and it talks about specifically also long distance propagation. A lot of the research that's being done these days is in terms of, you know, propagation at relatively short distances, like urban environments and so on. But when you look at long distance links, then you start looking at, you know, the influence of the climate and the weather, basically radio, what we call radio meteorology. And that's something that was not covered at all in my undergrad. I never heard of that, you know, about the K factor and earth bulge and looking at how the refractive index changes with different weather patterns. We never looked at any of that. And that was actually something that was so relevant because we design links that are over 100 kilometers long. And so you have to have an idea of, okay, this is, you know, going to be that far. At that distance, we won't have line of sight. We're going to have obstructions, and then look at, you know, all of those mechanisms. If you're in the desert, you need to know that, okay, then you're going to probably also struggle with that effect because of the specific weather patterns in the desert. And yeah, those are things that I personally would have appreciated, at least, you know, being made aware of, because it's not really complex. Even if you just explain a few different principles, mathematically, it's not complex at all. So it's something that is practical, and I think it's something that is interesting because it's a real world example of electromagnetics in action. So I think it is important for lecturers to look at that and perhaps speak to people from industry and you know, hear what these issues are that an engineer in the industry deals with on a daily basis, so that when they get to industry, they can say, oh yes, this is what I learned, and so that there's a link between those two.
Yes, yes, we should have a link together so that we know that this syllabus is actually going to be useful like industries. So I've looked at this in the chat area. There's no questions, but there's Hamdan, Lee Cheng, Jean said thank you. There's one question from Rashida Hanan. She said, thanks, Doctor, for the talk. Can you give an opinion on working in research institute? Where do you think it heavily falls into academia or industry? As you know, some research institute do have the collaborations between both. So
I think in some cases that's the best of both worlds. It's a little bit of both. So I think some of the principles definitely that I mentioned today will be applicable, but I think a research and development environment is nicely in the middle. So I definitely recommend, like I said, Mike Golio's article on technology maturity and other hurdles. He gives a very nice overview of the spectrum from proof of concept to mass manufacturing. And so a research and development environment is still way more towards the academic side. If you look in terms of volume, for example, you're still looking at relatively small volumes. Whereas on the other extreme, you have mass manufacturing, where you have, you know, millions of units being manufactured. There's a whole spectrum, but the research and development environment would still probably be a little bit more towards the academic environment. But the big advantage there is that you have a closer link with industry, and so you have the opportunity to make sure that what you're developing is relevant to industry.
All right, great answer. I hope it's yeah. Thanks for your insightful answer, said Rashida. Any more questions from members of the floor? Maybe you can turn on your mic and you can ask directly to our speaker. Oh, sorry. Okay. Dr. Henry just share a document, I3E.
Yeah, that's the one I just mentioned. Yeah. If you want to have a look.
Yeah, technology maturity and other hurdles, strategic planning for emerging RF consumer products. Oh, okay. Nice. Thank you, Dr. Henry. So we already reached 4 p.m. in Malaysia, Malaysia time. If there is no more questions, can we take a group photo, just for memory? So can I hope that everyone can turn on your camera so that I can take a group photo for everyone. Ah, nice. Let me stop recording first.